continue with some more exact algorithms. So what is exact algorithms? Exponential time algorithms we will design for some of the problems. Okay, but we try to do better than the trivial algorithm that we know, like 2 power n, which we know for a lot of problems we can just give it right in one line. So we try to do better than 2 power n, but in terms of the number 2. So we try to improve this number 2 and get something better there, right? And yesterday Arithro taught some of the algorithms for some of the algorithms in this manner. So we'll see some more today. Okay. So let's start with the dominating set problem. So in the hardness section, I did some reduction for dominating set, right? Anybody remember what was that? At least do we remember the problem? So as an input, we have a graph and we want to dominate all the vertices or cover all the vertices. How? By taking either the vertex itself in solution or one of its neighbors. This we all remember, right? So that is why whatever the solution is, its intersection with closed neighborhood should be non-empty. Yes? And here I will use this vertex set as small n and edge set as small m. Okay? The size of them. And we saw that 2 power n was this brute force algorithm, try all possible subsets, and we get it. Okay? And the other day, we gave a reduction from dominating set to some problem. Do we remember that problem? Anyone? No, dominating set to something. No. That was another covering problem. Huh? Set cover. Right? So if you guys remember, dominating set is very similar to covering something. So we reduced dominating set to set cover problem. And what the goal of today's talk is, exploit this reduction to get better algorithm for dominating set problem. Okay? So reduction is not just useful for proving some hardness, but we can also use them for giving a better algorithm. For example, reducing independent set to triangle finding problem, right? It is again a type of reduction. Whatever it took exponential time, but it is a reduction. And then we solve the triangle finding problem and we give a good algorithm for independent set, right? So that is what we will do for dominating set as well, but we will use set cover problem. Okay? So what is our aim for the dominating set problem? Can we get better than 2 minus epsilon power n? Okay, 2 minus epsilon, even 1.999 is better than 2 power n. Okay, 1.999 power n is also better than 2 power n. That's our aim is, but we will try to do as good as possible. We will not give the best possible algorithm that's known right now, but we will see something good. Okay? Okay, great. So let's recall our set cover problem as well. So what happens in set cover? What is the input? Family. Family of sets over some universe U. And what are we trying to cover here? Universe. Okay? We are trying to cover universe using what? Sets in the family. Okay? So we try to find minimum such sets, minimum number of such sets that cover the universe. That's our set cover problem. And again, if n is the universe size and m is the family size, then 2 power m is very trivial. Just try all possible subsets of the family. One of that should be minimum and should give you should cover the whole universe. Yes? So this is what we have. But the other day, I also gave you a dynamic programming algorithm for set cover, which does not have the family size in the exponent, but it have to power the universe size. So we saw 2 power n dynamic programming algorithm for set cover, right? Anybody remember that? So let's go back to problem definition. Does anybody remember a 2 power n algorithm for set cover? There was a very small idea there. Yes. Exactly right. So we just order these sets in family, and then we start from the end, and then we say, okay, do I take this family in my solution, or do I take this set in my solution, or do I not take in my solution? Depending on that, if I take the set in my solution, then I reduce those elements, I take out those elements from my family and increase my solution size because I am taking something in solution. Otherwise, what do? We just remove the set, and then we try to find a subset in the remaining family that cover the universe. That's what we did, right? So let me just write it down again. So let's say this is my family F1, F2, F3, Fn, and what does my DP table will store? So I'm calling DP table as op table. So it will store for every subset of universe and number I, minimum subset of F1, F2, Fi, that covers this subset. Okay, that's what we are trying to store in our table. And how do we do the computation? For base case, it was easy. If I just have, say, one set, if we are at F1, then all we have to check is if U star is subset of F1 or not. In that case, we set it to 1. Otherwise, we can set it to infinity. Okay. So this is 1. Otherwise, it is infinity, right? And how does the recursive step work? So opt of U star I is as she said. So either we take the family, take the set into the solution, and we take out those elements, and then we recurse on the remaining. So I am adding +1 here because we decide to take Fi in the solution. And otherwise, it is opt of U star, comma, I minus 1. And we take the minimum of this two quantity. Right? That's how we store, how we compute the DP entries recursively. Okay? That's what we are doing. So, one thing to notice here, I am storing some numbers, right? How do we get solutions out of these numbers? So suppose instead of what is the minimum solution size, I want to output the solution itself. Instead of saying 5 sets can cover it, I want to output who are those 5 sets. Then how do I find it out? Yes. And in every dynamic programming algorithm, you can use the trick of backtracking. Just backtrack where you are getting the solution from, and then you can construct the solution. You can use this trick in any dynamic programming algorithm. Okay? So here also I can just do the backtracking, and I can find out what are those subsets which gives me the minimum size and cover the universe. Okay? What is the running time of this algorithm? 2 power n. Into some polynomial multiplication. Why 2 power n? Because I am storing an entry for every subset of universe. How many subsets are there? 2 power n subsets. And 2 power n into I is m. So how many choices I have for I? M many choices, which is the family size. Right? So the total number of entries are, I'll write it here, 2 power n into m, and to compute each entry, how many entries we are looking at? We are looking at 2 entries, right? So that takes some constant time because we will just go to those entries, and since we are computing it recursively, the smaller entries will already been have computed. So we can just go and take the values of that, put it and compute the bigger entries, right? Okay, so this will give me some order n into poly, not order. Yeah, so this gives me some 2 power n poly in m plus n algorithm, right? But this idea that take this set into solution or not, we will exploit it for improving the running time as well. Just remember this idea. And also this idea that order things and then go one by one. This is also important. We will use that idea as well to design some more dynamic programming algorithm. And this idea you can use in a lot of problem. That first order and then just take something or don't take something. I think Hamiltonian cycle or Hamiltonian path problem also use something similar idea. Okay? Okay, so this is what we did in the previous class. And that gave me something in 2 power n. Okay? So I have one algorithm which is 2 power m. I have one algorithm which is 2 power n. Now I want you to think of an algorithm which is way better than that, but the exponent is n plus m. Okay, so I am giving you something 1.3803 power n plus m, but here it is the exponent is n plus m. Okay, so here this was capital N and capital M. Okay, so we have seen some branching algorithm, right? Where what do? We decide either take it in solution or don't take it in solution. If we don't take it in solution, then something else happen. Right? So those type of algorithms we have seen. For vertex cover we saw take this endpoint or this endpoint, right? And then in exercise also we saw like for vertex cover itself that okay, take this vertex or take its neighbors, right? So we have seen this 2 guesses or multiple guesses type of algorithms. Let's try to do something similar for set cover. Okay? But we will use the same idea. A set goes into the solution or it does not go into the solution. Okay? But now, what will be the measure of our running time? What we are decreasing? At each step, when we say take this in solution, what is our measure? What do we decrease? So in each of such branching algorithm, there is a measure, right? Either it is a budget or something else. So in vertex cover, what was the measure when we said take this vertex into the solution or this vertex? No. The solution size was our budget. The measure was our solution size, right? And in each of the branch we say this the measure is strictly decreasing. So it will not be the case that we take more time here, we will take less time only in terms of the measure. Okay? So here our measure will be n plus m. So we want to decrease at least one of the quantity, either n or m, or if we decrease both, then also it is counted the sum of them in our measure. Okay? So let's see. So let me call the measure as mu and I'll write it as n plus m. Okay? Okay, so now let me do some pre-processing here first. If I have sets of size 1, what can I do about them? Should I include them into solution? Always? When should I include it, like definitely? If that element is not covered by any other, is not participating in any other set, right? So suppose I have a set F which looks like this, but U is not in any other set. In this case, I know I have to take this set in solution, otherwise I cannot cover this element U, right? So I will just take F in solution. And here we are talking about optimal solution, that means minimum size solution, so we don't have any budget or anything to decrease. Here there is no guessing we are doing. This is a deterministic step, right? I have only one choice and I am making it, and this is a polynomial time step. I am saying if U is not appearing in any other set, it only appears in exactly one set. That's true. that's true if the element appears in one set, whether its size is 1 or 2, it does not matter. But what I am trying to do here is go over the set sizes. So we started with set size 1 and we are doing something on them. I am not talking about other set sizes. Okay? So this is what we did. Otherwise what happens? U is appearing in some other sets as well. What should I do in that case for this set F? Can I simply delete it? I can, right? Because if this goes into the solution, I can take that other set that is also containing U.
There is some other set which cannot have U, and I can take that set and union as an optimized solution. Maybe the bigger set which have a U cannot be in optimized solution.
So we don't take the union and take the optimum. The number of sets is what contributing to my budget. Okay? So just by replacing one set with other set, we are not losing on solution size. Right? Because we will take out F. Its only job is to cover U. But when I take it out and add some other set which also covers U, then I am not changing the solution size. Right? So that's what happens if U belongs to some other set F star. So here F star is not equals to F. Then delete F. So if I have a solution, say S, which is subset of family, and F belongs to S, then what I can do? I can take F out of S and I can add F star. So maybe F star is already present in S. In that case, I don't need to do anything. The solution strictly decreases. Otherwise, I just take out one and add one. Right? So the solution size remains the same. I am still giving you optimum solution. Right? So suppose this is some optimum. So this is if I have set sizes 1. This is easy? Okay. Yes? Okay. So in the second case, if U is participating in some other set F star that is not same as F, it can have any sizes, 1, 2, 3, any size. Okay. Now I am saying I will simply delete F in that case, the set F. Okay. And when I am deleting it, how am I telling you? See, you still have an optimum solution that covers everything of the same size. If suppose there is an optimum solution S, if it does not contain the set F, then anyway it is a solution after deleting F as well, right? Otherwise, it is not a solution. Why? Because F is contained in the set and that is covering U. But then I can replace the set F by F star and then I can get either the smaller size solution or same size solution.
Either F is the set of only U.
Yes, that's what is written, right, in the second line, that F is the set which only contains U. Otherwise, we are not saying anything. Because what is the job of F? It's to cover U, right? It does not have any other job. If any other set can do the job, then we will take that set. That might cover more elements, not just U, right? So this is dealing with one size sets. Now, I want you to deal with two size sets. And then if no such sets are there of size 1 or 2, then every set have size at least 3 or there exists at least one set of size 3. I would like to branch on that. Okay, so size 1 set I have taken care of. Now my claim is either there are no, if there exists a set of size at least 3, then I will do something on those type of sets, the branching. Otherwise, I don't have any sets of size at least 3 and I will solve it in polynomial time. If I only have sets of size exactly 2, I solve it in polynomial time. Okay, so either there exists a set of size at least 3, that means there is some set F which contains at least 3 elements. Otherwise, all sets in F have size exactly 2. because one size sets we are getting rid of them, right? So in this case, my claim is solve in polynomial time. Okay, so why it is solvable in polynomial time? You can think of it as another problem which is called edge cover, basically covering vertices using edges, okay, and which is polynomial time. Unlike the vertex cover where we cover edges using vertices, when we look at edge cover where we are covering vertices using edges, it is polynomial time. Okay, so I will leave this part as an exercise. It is not very difficult to think. You just have to give a reduction to edge cover problem. Basically construct a graph and tell me that if I use minimum edges to cover all the vertices, then I can use it as a solution to set cover. Okay, so here I have a graph and the goal is to find minimum edges that cover all vertices. Okay, so give reduction from set cover. Let me call it 2 set cover because every set have size 2 to edge cover. Okay, so this is what you have to do. So either I have set sizes 1, then I am dealing with them in polynomial time. Otherwise I have set sizes only, I have only set sizes 2, then I will deal with it by using edge cover problem. Think about how you will do it and then we can discuss later as well. Okay? Okay, so if I don't have any of these 2 conditions, then what do I have? At least one set of size, at least 3 elements of size at least 3. Okay, so let's say there exists a set F such that size of F is at least 3. Now in this case I will do the branching. Till now we have only done polynomial steps, right? And now this is what will give me that exponent running time, 1.3 something. Okay, so what do we know about any set? What did our DP algorithm exploited? It belongs to solution R, does not belong to solution. There are 2 cases only, right? So let's do that for this set F. F belongs to solution, F does not belong to solution, right? In first case what happens? If F belongs to solution, then from whatever our current universe is, yes, so we remove the elements of F and we remove the set F from the family. Here we are not going from the ordering, we are just picking a set which have size at least 3. So I am not writing I here, we are just removing this set from the family, right? So I have, yeah, this should be a set notation here. And in the other case, when it does not go to solution, we just remove it from the family, right? These are the 2 branches we have. Is it correct? And we know that if there is a minimum solution, so here we had u comma f. So whatever the, you can also show here that if I had a optimum solution of size something, then one of these branches should be able to help you to reach that optimum solution, right? And if you can solve one of this, then you can get an optimum solution to F. You can prove the if and only if condition here, like u comma f, if and only if one this or this, right? So that you can prove. Okay, so basically what I am trying to say now, okay, let's first do the running time calculation. So what was our measure? N plus M, What happens in first branch? How much does the measure decreases? Huh.
If F belongs to the solution, then we can remove all these sets that have at least one element.
We can remove all the sets.
That have at least one element that is in F.
Yes.
Then why do we remove only F?
Okay, so yeah, you are right. So we are not just removing the set F, but we can also remove those elements from F from the other sets. So I should not write it as this. Let's say we are constructing a new family F star, where what do we have? All the sets F star minus F,
Removing from
no, we can read the family, right? Reading the family is part of the input. The family size is part of the input size. So you are confusing same as the number of clauses can be exponential. We are reading it and taking exponential. No. That is part of my input. The family is part of my input. I can read it polynomial many times. So this is, one second. I have written it other way round. So this is F star minus F such that F star belongs to F. This is what we are writing. And we are taking out the set F that will give the empty set. Okay, why will the set size, why will the number of sets increases here?
Yeah.
Corresponding to every set in F, I am only adding one set. I am not adding any new set in F star. So sets will remain same. It will only decrease, right? Because one set is completely gone, the set F.
No, what I meant is that if we, we are saying remove, but doesn't necessarily mean that we would also add those to the set cover.
Where? In solution you mean?
Yeah.
Which sets are we adding in solution? I am only adding set F in first branch in solution, not the other sets.
But what if,
That's taken care by the other branch. It does not belong to it.
No, what is your question?
I was about to ask what if the other element in the set which has
Wait, what?
some other element of the sets which are covered by F happen to cover some other sets, but yeah, I realize.
I am not removing any set, right? I am just removing elements of set F. Right? F star minus F, these are just two sets. That this is like a different F, that is a different F.
So we
Okay?
are just removing elements from
Yes, we are just removing the elements, not the sets. Okay? Okay. So this is what I have. So what, anybody have any other doubt in this branching? What happens in the first branch? What is the decrement? How much decrement I am getting? Yes.
I have one doubt.
Yes.
If I remove the element from all other sets, I will be comparing the give optimized combination of sets.
See optimum, what is the optimum solution? Solution is number of sets, right? So suppose there is another set, it have already covered, it might have already covered elements, or it might have some new elements, right? But I am only adding that particular set. I am not adding two sets instead of one set, right? Yes? So if F star was in solution, I am adding F star minus F, but can't I just add back the element? I won't increase the solution size, right? Because firstly we are removing the elements of F from universe. We are not trying to cover all the elements we have covered already. So now every time we are trying to cover new elements, right? In this particular branch. And we are keeping the sets in a way that only cover the new elements, which is in U minus F. Okay? The one thing to do here is take a solution and construct a solution here, take a solution here, construct a solution for UF and see if the solution works. Okay, so maybe I can give you an example. Suppose there is an optimum solution S, okay, and it is covering the universe S for this instance, and if F belongs to S. Then can you give me a solution to U minus F, F star using S? What will be your solution? Just by using the set S, can you construct a solution to U minus F, F star if F belongs to set S? What will be that solution? What will it be? So, you had a doubt, right? Can you construct a solution? So, I have some sets in S, right? Say F1, F2, Ft. Okay? One of this set is F. Say F2 is that set F. Okay? How will I construct? Now I need to cover here only U minus F. I don't need to cover F, right? So what will I do here? I will take F1 minus F, F3 minus F, and so on, Ft minus F. Right? This will cover U minus F, and all of these sets belong to my F star. That's how I constructed F star. Right? And in the reverse direction, wait. So let's prove the optimality here. Okay? Suppose now whatever your solution to the reduced, so you are saying maybe you are constructing a smaller solution for the reduced, is it? Okay, let's construct that smaller solution. You have some optimum solution which will be of minimum size. Okay? So let's take that solution. Let's say S star is minimum solution to U minus F, F star. This is some solution. Okay, say I have some sets F1, F2, Ft. This is my S star. Okay, now I can construct the same size plus F solution for U comma F. So give me a solution which is S star plus 1 for U comma F. Can you give me a solution? We just maintain one solution. We don't maintain every solution firstly. Even then you can maintain every solution in this reduction. This is one, I am picking any minimum size solution. I didn't specify what S star will be, right? These are any F1, F2, Ft that is a minimum solution. For any minimum solution, I can construct you a solution which is just plus 1 size. Right? Is it fine now? So I am not altering with optimality. And the thing is, I am trying both the possibilities. When U belongs to solution, when F belongs to solution, when F does not belong to solution. Right? So one of them should be correct, right? I am exhausting all my possibilities. It is not the case that only one choice I am making here. I don't know, maybe F is in solution, maybe it is not. Right? Now is it fine with everyone? And I just gave you a correctness by doing all this. So I hope you are able to construct S star plus 1 size solution. You just have to add the set F to whatever if you have removed it from there. Right? That's what you have to do. Okay. And if the other branch is correct, then again you can do the similarly. You can construct the solution. Basically you give the same size solution in the other branch. The same solution you can return because the family is subset of the family F. Right? Okay. Any doubts till now about the correctness of why this branching is correct? Anyone? This is fine now, right? And this is a very good thing because any branching algorithm you see, you can prove the correctness like this. If I have a solution here and this branch is correct, I can generate a solution like this. You should be able to generate the solution. And if you get a solution here, you should be able to generate the solution to the original instance. Same with the other branch. And one of the branch is correct, so you should have the solution. The branching should be exhaustive. Okay? Yes.
If I don't remove the elements from the F,
yes.
then it also be the optimized solution. I will not be adding the.
So here I am using the fact that the set size are at least 3 and they are covering the new elements. That's how I want to do in order to give the good running time. Yes, then I don't decrease anything, but to avoid that, I am taking out those elements so that every time I cover new elements. That's fine, because all I am trying to do is make the exponent factor better. There is a polynomial multiplication here, but it is only a polynomial multiplication. I can use that. Okay? So anyway, exponential is way large than the polynomial, so we allow that much to us. Okay? Okay, so we keep doing this, and how does our measure decreases in first branch? 4, right? Because 3 elements at least are taken out of universe, and these 3 will be new elements because we get rid of the elements from each set when we cover it, right? So every time we are covering at least 3 new elements. So u minus f decreases, the size of u minus f is decreased by at least 3. Okay, and the measure is size of universe plus size of family, and the family size also decreases by 1 because the set f is taken out of the family, right? So here the measure decreases by 4, and here the measure decreases by 1, right? And we can compute the running time by this formula. Okay, and when you solve it, you will actually get the running time 1 point whatever that power n plus m. Okay, do we know how to solve these equations? Okay, I will tell that in the next session. But my claim is, if I have 1,4 branching, then I get this running time, and which is what we were looking for. Okay, so I have this, and I get this running time for my set cover algorithm, and I will do it repetitively. Okay, so anytime I encounter first case, set 1 size, I apply my rule, get rid of them. Anytime I have at least 3 size set, I will apply the branching. Once I am done with all the at least 3 size sets, I have only 2 size set remaining, and then I solve it using edge cover. Okay, that's all my algorithm. Okay, yes? Yeah, so 1 and 4 is, just 1 second. Yeah, so in one branch, I am decreasing 3 elements from universe size n decreases by 3. In the second, 1 set is removed, so the family size decreased by 1. So m decreases by 1, so n plus m decreases by 4. And in the other, only family size decreases, so m decreases by 1. Okay? Okay, so let's not spend more time here. But as you can see that I had some 2 power n, I had some 2 power m, but by combining both this, we are getting something like 1.3803 power n plus m. Okay, that's what we are getting. But how do we exploit it to get a good algorithm for dominating set? Let's see. So we all remember the reduction from dominating set to set cover. Basically, what do we do? How do we construct the universe? It's just a vertex set. And how do we construct the family? Close neighborhood, right? So we add close neighborhood of every vertex to my family. That's how I construct it, right? How much time I took for this construction? Polynomial time. Again, reading the family takes only polynomial time. The family size is a polynomial for us. Okay, because we say polynomial in input, and family is also a part of an input. Okay, so this is what we have, and what is the size of u here? N. Size of f here is also n, right? Because for every vertex we only add one close neighborhood, right? So this is fine. We have discussed this before as well. Any doubts here? Okay, great. Now let's see what does this reduction implies. I have 2 algorithms for set cover. One was 2 power n, but n is n for us, small n for us. So we get 2 power n algorithm for dominating set, but that's not very interesting. With the other one, what I can do, I can take dominating set, reduce to set cover in polynomial time. I can run this algorithm which we just discussed, which have n plus m, and what do we get? N is n, m is also n, so this power 2n, which gives me something like 1.905 something something. I have just written it as 1.91 power n. Right? Just by using this reduction, I got an algorithm which runs better than 2 power n. I get something like 1.9, right? Which is very interesting. Now anytime you improve a set cover algorithm, this number, you can get a better algorithm for dominating set. And for that matter, whatever problem you can reduce dominating set to, if you maintain this n and m, and in terms of whatever running time you get, you can get a good algorithm, right? Okay, so good, that's interesting. That's all I wanted to say about how to get a good algorithm for a dominating set using set cover. Okay. Now still this is 1.9, right? Why can't I do better than 1.9? Is it the best we can do? Or we can use some other tricks and techniques to get something better? So firstly, dominating set is a very weird problem. I can't do simple branching like for vertex cover, take this in solution or take this in solution for every edge. For dominating set, what will I say? If you take a vertex in solution, what all to delete, I don't know. Because its neighbors are covered, but those neighbors can help cover other things. Right? Similarly, if I don't take it in solution, then what can I delete? I don't know. So those type of trivial things I don't have for dominating set. Therefore, we are going via this other routes. Okay? Okay. So now this we have exploited. Now I want to exploit the vertex cover algorithms or the vertex cover problem to get good running time for dominating set. Okay? And what I want to do first is for dominating set, give an algorithm which runs in 3 power vertex cover time. First thing, I have one question. Can you tell me if a vertex cover is also a dominating set? Maybe not of small size or the smallest possible size, but is vertex cover also a dominating set? Yes or no? Yes? Why? So I have some vertex cover vertices here, and then I have some independent set vertices. How does all the edges of the graph look like? Either within vertex cover or across. Right? These are all the edges of the graph, and that's all the graph looks like. Right? Huh? No. So that will be part of independent set, right? Okay, yeah. You are talking about the dominating set. Yes. Okay. So can we say a vertex cover is also a dominating set? The question. And SG mentioned if there is an isolated vertex, then we can't say it. Right? If there is a vertex which have degree 0, then we can't say it. But we can always get rid of those vertices by taking into solution, right? They are always part of the solution. Yes? But otherwise we can always say a vertex cover is also a dominating set. Yes? This is fine with everyone, this observation? Okay, now I have other question. Is maximal, I am using maximal term here, independent set a dominating set? So what does maximal mean? I can't add any more vertices to it. Otherwise, I'll break independent set property. That's what maximality mean here. This is the maximum. This is the maximal set I have. If I add one more vertex, it will have edge to some other vertex in the maximal independent set. Yes, that's what maximal mean. Can I say a maximal independent set is also a dominating set? Yes? Yes, right? Because every vertex have at least one neighbor in that maximal independent set. Otherwise, I can add that vertex to my set and I can get a bigger size set. Then the maximality is broken. Right? So every maximal independent set is also a dominating set. Okay? Okay, but we will exploit this fact. A maximal independent set is a dominating set. And then we will try to design some good algorithms for dominating set using vertex cover. What we will do? First we will design some 3-power vertex cover, and using some similar ideas we will design 2-power vertex cover. Okay, that's the aim now. Here we are not trying to design an algorithm for vertex cover. We are just exploiting it. We are just exploiting the structural property of graph when we have a vertex cover given to us. Okay, that's all we are doing. But we are solving the dominating set problem. Okay, so instead of looking for 2-power n, 3-power n something, we are looking for 3-power vertex cover size. This vertex cover is given to us. We know what it is. Okay, is fine with everyone? Okay, great. So let's see what we can do. Okay, suppose I have a vertex cover, say set X, and then I have the remaining vertices. I am calling them, say I. I is what? Vertex set minus the set X. Okay, so this is what I have. And I have some edges which can go across, some edges I have here. Okay. Now remember when we were trying to solve vertex cover problem by some modulator, we did this step that we can do some guessing from the set X, right? And since we are only spending something like going over all the subsets, we can do that for if we are looking for something like 2-power x running time. Okay, so here let me call it vertex cover, the size of x. Okay. Okay, so what I want to do from the vertex cover, first I want to guess what goes into the solution, what does not go into the solution. Solution of dominating set. This I can do. How much time I am spending here? Going over all the subsets, which is 2 to the power vertex cover. Yes, it's fine with everyone? Yes. So let's do that. Let's guess the set which goes to solution. This goes to solution, the remaining does not go to solution. Okay, so let's give it a name. Say J is subset of X, J belongs to solution of dominating set. And since we are trying all such set J, one of the set will be part of the minimum dominating set. Let's talk about that particular set. When we go over all, at least one of that is good for us. Okay, so we have guessed that J is part of solution. Okay, let's say D is not part of solution. It's not part of solution. Okay, what can you say about neighbors of J? Are they all dominated? Yes, right? What can you say about the vertices which are not neighbors to J? They are not dominated. What about those type of vertices if they are in independent set? They become part of the solution, right? Because I don't have any other edges from independent set to independent set vertices. All the edges are coming from vertex cover to independent set. And if there is a part which I don't take it in solution and a vertex is only neighbor to that no part, then I have to take that vertex in solution, right? Okay, so what I am trying to say is, suppose This green part is not going into solution. Okay, they should not overlap. So this green part is not going into the solution. This pink part is going into solution. Okay. Now if I had a vertex which had all the neighbors only in green part, what happens to that vertex? It have to be in dominating set, right? Otherwise I can't dominate it. And since we are going over all the guesses for J, then suppose we have guessed correctly that only intersection is to the solution, only intersection from X to the solution is J, then this vertex must be part of the solution, right? Everybody agrees on that? Okay. So let's construct a set. Let's call it S. S is equals to, at the beginning it is J and neighbors and I minus neighbors of J, right? So which are non-neighbors of J. So these are all the vertices that have been that are part of the solution. And what is dominated by this? Neighbors of close neighborhood of S is dominated. Okay. So now what is remaining to dominate? So independent vertices are all dominated or not? Yes? Is there any vertex in the independent set that is not dominated by taking this set? Isolated vertices, they are part of independent set. Okay? It's fine. So I have taken them. Now what is remaining? Some vertices in vertex cover that are not dominated. What are those vertices? That are firstly inside green, second, they are not neighbors of J, right? So now, what is to dominate? Let me write from to dominate X minus close neighborhood of J. This is the set. So I have some neighbors here, those are dominated. Then something is remaining here, not just that. Yeah, so even their neighbors, this is also dominated. So suppose this is the part which goes to solution. Let me also make it pink. So all the neighbors of pink is also dominated. All the neighbors of this pink is also dominated. And there is something remaining which are not neighbor to anything which goes in solution. Okay? Fine. So this is what I have. Okay. Fine. Here. So this is close neighborhood of S. X minus close neighborhood of S. That is what I need to dominate now. Okay. Do I know any algorithm for dominating set with what we have discussed? What can I do? I just need to dominate them. I can make a new graph now. What is there in the graph? This, yeah, only this set of vertices, which is, let me call it something, let me just write it this way. And then I can keep all their neighbors, right? They are dominated, I don't need to dominate them, I just need to dominate this part. Okay? So this is the vertex cover ka subset and this is independent set subset. Now can I reduce it to set cover problem? How do I reduce it to set cover problem? What will be my universe? The set above, right? How will I construct the family?
Yes, between the vertex cover subset and the subset after.
Can there be any edge between independent subset, independent set subset?
Between the two.
They can, there will be or there can be.
Wouldn't it be found in previous?
These are not part of solution. They can have edges, right? But these are not part of solution, these are not part of solution. If they were part of solution, then those vertices are dominated, their neighbors, right? These are all the vertices that are not yet dominated.
Yes.
Yes? Yes. But then, yes, ask. Okay. Yes, it's just, okay, so let me say it here. So these are the parts which is not colored pink, and this is the part which is here, which is not yet dominated. So I am just extracting this graph, and because everything in pink belongs to solution, that should be set S, part of set S. Here this is also part of set S. Everything is dominated in independent set, but everything is not part of solution. Right? Everything in independent set is dominated, but I am not saying all of them is part of solution. What is a part of solution? Only the vertices that were not neighbors of J. Those are part of solution. Those are neighbors of J, they are dominated, but I am not saying you must go into the solution, right? That's what we said. Is it clear or is it confusing?
So the remaining vertices are the ones which are in the green part and those which do not have the neighbors are
Yes. So just to recall, I choose a set in J in X in the vertex cover that goes to solution. So all its neighbors, wherever they are covered. Now there are vertices which have only neighbor in no part. They have to be part of solution. So we took all of them in solution. Now there are still some vertices for which neither the neighbor from independent set goes in solution, neither the neighbor from vertex cover goes in solution. We still need to dominate them, right? So those are the vertices I am taking here, and these are the vertices from independent set that are not yet part of solution, right? They are dominated but not part of solution. Dominated meaning I don't have to pick a new vertex to cover this or dominate these vertices. I can use them to dominate the vertices which are not yet dominated, right? I cannot pick anything from this set because I guess that this is not part of any solution. So I have to dominate them by taking vertices from independent set which are not yet part of solution. Does it make sense to everyone? The part of the no solution guess and which is not yet dominated. Yes? This is clear with everyone? Okay, now give me a set cover reduction from here. The universe is the set which is not dominated. What is family? Close neighborhood of the independent set vertices, right? So, let's write it here. So suppose I have a set, let's call it X star here, and then I have an independent set, let's call it what? Some Z. Okay? So my universe will be, so this is vertex cover and these are independent set. I don't have any edges here. All the edges looks like this. And I don't want to dominate anything in Z. I only want to dominate X star. So my universe is X star. Okay? And my family is close neighborhood of V such that, not close neighborhood, open neighborhood. This is open neighborhood because I don't have to cover the vertex. So I don't need to include the vertex here in the family. So open neighborhood of V such that V is in Z. This is my dominating set construction. Right? Everybody is fine with this? What is the size of this family? Atma is the size of independent set. What is the size of universe? At max the size of vertex cover. Vertex cover. Do we know any algorithm for set cover which runs in 2 power universe? We know, right? We just did a dynamic programming algorithm. Right? Which runs in what? 2 power size of universe. The first ever algorithm that I said today. This one. Right? So we can use this and we can solve this reduced part in how much time? 2 power size of X star. Time by using set cover. Anybody lost till here? Everybody is fine? Okay. So now whatever this returns, I can just combine this solution with the set S and I can return the solution. Okay. So let's say set cover returns S star, then my dominating set will be S union S star. Okay. and you can prove that this is the minimum solution. And you can go over all the sets J and take the one which minimizes this. Okay? Take J which minimizes this. Okay, that's what we did. Okay, now the running time computation. This take 2 power x star, but what is the total running time? What is the total running time in your opinion? What is it? So we go over all the vertex cover that are 2 power vertex cover. Then we apply 2 power vertex cover again to solve the reduced instance, right? So is it 4 power vertex cover, or we can do a better analysis? What about if I write it this way? So running time will be summation of Can I write it this way? What is step 1 doing? Just taking a subset and then doing some steps in polynomial time. Delete this neighbors here, delete that neighbor here, and that's all. Right? All those is polynomial time steps. If I have the knowledge of which set I am taking. And how many sets I have? Summation I equals to 0 to vertex cover. Vertex cover choose I many sets. Right? And for each such set we are taking 2 power vertex cover minus I at most running time by set cover algorithm. What is this? Does it look similar to something you have seen before? What is it called? Binomial theorem. What does binomial theorem says? Summation I equals to 0 to n choose I, x power I, y power n minus I is equals to x plus y power n, right? So let's compare this with our running time. Vertex cover choose I equals to 0 to vertex cover 2 power vertex cover minus I. What term is missing? This is missing. What can I write here? 1 power I, right? Because the polynomial multiplication we can write it outside, right? What does it give me? 2 plus 1, 3. 3 power vertex cover into polynomial in n. So just by doing a better analysis we get this running time. But the algorithm is same. Guess a set, then solve set cover. That's all we did. Okay? Okay, so we still have some time. I will take 5-10 minutes extra and give you a better algorithm. Okay? So I can solve it in 3 power vertex cover time. But here what are we doing? We are doing this set cover for every set, right? Maybe we can do something better here. Why do I need to solve this set cover again and again for every set? Can I do some faster algorithm that at one point itself, if I know this set is not going into the solution and I have to dominate it by its neighbors, then why don't I initially consider all such sets and compute the best dominating set I can get for them? Can I do that? So basically what I am trying to say, suppose you know that there will be a set D which is not part of solution and you have to dominate it. And it is a subset of vertex cover, right? So why can't you just consider all such subsets and at the beginning itself compute the best dominating set they can get? And their dominating set is coming from independent set, not from vertex cover, right? So for all subset D of X, compute dominating set for D, that is subset of independent set, which is Vg minus x. Can we compute this? Now my claim is I can do it in 2 power vertex cover time. Basically, what should I do here? Can I do a dynamic programming? How do I do a dynamic programming here? I know one way of doing dynamic programming. What is it? Can I talk about set cover again here? What is the set cover dynamic programming did? Order the families, order the sets in family and then guess either you are part of solution or not, right? So it is just the same dynamic programming algorithm. Now instead of looking at it as a family, you can look at it as the vertices in independent set. But those again you can consider as family, you can write it as a set cover instance, and those sets, those vertices in independent set will give you a family, right, just by taking their close neighborhood. It's the same reduction that we did above here, right? So basically now what do we want? We want to cover our universe, which is D. But why do I need to write it as D before? What does the dynamic programming table computes for set cover? It computes the minimum covering set for every subset, right? So it is inbuilt in the set cover dynamic programming algorithm here that I am computing for every subset here, right? I go over all the subsets, I go over all the i's, 1 to m. So this itself give me for every subset what is the minimum dominating set I have, right? Everybody can see that? Or is there any doubt? Okay, so what I am trying to do now, compute these sets by running DP algorithm of set cover. Okay, so I'll just look at this as a set cover instance, and then my set cover dynamic programming algorithm have this inbuilt property that for every subset of my universe X, it will compute the minimum dominating set, right? That's what it does. And how much time it takes? 2 power universe, which is 2 power vertex cover. Now I have a dynamic programming table stored for me. I can just go and take this entry from there, right? Yes.
Value of that. We have a close neighborhood of vertex and plus vertex.
Not the vertex. So we will get rid of the independent set vertex because we don't want to dominate that. We only want to dominate the universe, which is vertex cover vertices for me. So I will take open neighborhood here. So just like we did in the previous case, I will construct the universe as set X, and my family is open neighborhood of V such that V belongs to independent set. Okay, that's what I am doing. And then I will just solve the set cover but using the dynamic programming, the first dynamic programming that I explained, which runs in 2 power universe size. So here you can see that all the sets only contains the elements from the universe, not anything else, right? Yes? Anyone have any doubt here? Everybody looks lost. Any questions? Just ask questions. Okay?
Only way we can reduce the size of F.
What?
It is the only way we can reduce the size of F.
Size of F. I am not reducing the size of F. I am just writing what I want from my instance. Size of F is independent set size. But the running time we are using is not in terms of family size. It is the first dynamic program which run in 2 power universe size. So family size can be anything. It is here, it is vertex cover minus the vertices minus the vertex cover vertices, right? So this solves in 2 power x time, which is 2 power vertex cover. Okay. So in this much time, for every set, I have stored the best dominating set. So if I know this, for this set I have to find a dominating set, instead of solving set cover again, I'll just go to dynamic programming table and tell me that which is the best solution. I'll just ask the dynamic programming table. Okay. So what will be my running time now? I have run this algorithm beforehand. So this is 2 power vertex cover into polynomial in n plus, now I am doing the same thing again, right? Choosing a set, summation I equals to 1, 0 to n, vertex cover choose I. But now I am taking polynomial time to find the best dominating set for what does not go into the solution and does not get dominated, right? So this is something polynomial here, so I am not multiplying any exponent factor here. Yes? So what will be my running time now? 2 power vertex cover, because this is 2 power vertex cover, this is 2 power vertex cover, which gives me 2 power vertex cover n power order 1 algorithm. Okay, and how do I compute the dominating set? So firstly, I take this set S, which is J union I minus neighborhood of J set. This set we take and we combine this set with whatever the dynamic programming gives us for the set which is not dominated. So this will be some set, let's say this is some D star. For this D star, our dynamic programming will have stored some dominating set, right? We'll just go there and we just take that set and combine it with S and return. Okay, that's all we are doing. So we are doing a pre-processing, run a dynamic programming, store a lot of things, then run the algorithm. So we are saving a lot of time here. Every time we are not going and running 2 power vertex cover running time. Okay? So just a small trick, but it gives us this. Okay, so let me just take 5 more minutes and tell you how this 2 power vertex cover helps me in getting better running time for dominating set. I said one thing in the beginning, that maximal independent sets are also dominating set, right? So let me just observe 2 things. If maximum independent set is between this range, or not. So I have a maximum independent set which is at most alpha n, or it is greater than alpha n. I'll consider two options. In the second case, when the maximum independent set is greater than alpha n, what is the vertex cover size? 1 minus alpha into n, right? So this is what we know about vertex cover and independent sets, right? Okay, so if this is my vertex cover, the remaining vertices gives me independent set, and if this is I, this is n minus I, and vice versa, right? So if I maximize this, this is minimized, and if vertex cover is minimized, independent set is maximized. This we all know, right? So now if I am saying, if I have an independent set which is at least some alpha n, then vertex cover can only be at most 1 minus alpha n, right? So in this case, how will I solve dominating set? By running 2 power 1 minus alpha into n. Okay, we want to find out this alpha such that it minimizes this. Otherwise, what do we do? Independent set is at most some alpha n, and in that case I will go over all the sets of size at most alpha n. One of them is maximal independent set, because we are taking all the independent sets. We are computing all of them. So one such maximum independent set is also maximal, that will be a dominating set, right? So if I know the maximum independent set, which is also maximal, have size at most alpha n, then I can go over such sets which is n choose alpha n. Okay, this is going over all the independent set and finding a dominating set. Okay, okay, so this is what I have, but now I want to find out alpha which minimizes this two quantity. And it happens that when I set alpha something like this when I set the range for alpha something like 0.2271 and this, then I get the best value which is 1.7088 power n for both of this function. So this also becomes 1.70 power n, and this also becomes 1.7 something power n. So there is not any rocket science or magic here. It's just by using this entropy function which is giving me the best running time. So this is what is happening. All we need to find out is what is the alpha that optimizes this function. That's all. And maybe you can use some websites that will give you the optimal value. Okay, so now just by using this idea, but here we are using a lot of things, right? We are using 2-power vertex cover algorithm which uses the set cover algorithm and so on, but combining all this idea give me an algorithm for dominating set which runs in 1.7088 power n, which is way better than 1.9 power n. Okay, so that's all I wanted to say. Just go back and look at the notes. If you have any questions, you can ask me. Okay.